Hi, my name is Edna. I am from Mexico City. I study biology at UNAM, and I want to study the collective motility of a bacteria, which its name is Myxococcus hantus, but in a complex medium. So, the myxobacteria are recognized by the formation of multicellular aggregates called fructive bodies, and they can arrange in a diversity of structures, as you can see. They can be from simple mounds to branch forms, and these fructive bodies arrange in response to a specific environmental signal. One of the most studied myxobacteria are Myxococcus hantus. This myxobacteria has been studied from evolutionary, metabolic, ecology perspective, but always in laboratory conditions. But this bacteria inhabit soil. It's their natural environment. This Myxococcus hantus is characterized by its root shape. Also, they present a gliding movement, no? And they present a really complex cycle of life. One of these is a vegetative growth that it consists in the predation of other bacterial species, but at starvation, these bacteria start to form these fructive bodies with the collective movements of their cells. There are some signals that help them to know that this behavior will start. This is really good understanding in homogeneous mediums at laboratory conditions, but there are some recent studies that indicate that heterogeneous or mediums can change these behaviors that we know in these homogeneous mediums. So I would like to study these types of heterogeneous mediums with Myxococcus hantus. I would like to construct some two-dimensional simulations in Compusel and prove the effect of put some physical obstacles and just with implement really a few energies just to see this collective movement. No, I just want to prove in a specific moment in a specific moment of the cycle life. I don't want to see all of the complete cycle. Just I will see in the collective movement of the cells, in the structures of these fructive bodies. A very characteristic feature of these bacteria is that they stretch a wall of polysaccharides, that these polysaccharides can can be followed by other bacteria. So in this way, they can follow up within really, really easy. So this is one thing that I would like to, to see in my simulations. Also, I would like to prove two types of cells, compact cells and elongate cells. As you can see, and as I mentioned before, these bacteria present a round shape. So I want to know if the shape of the cell can modify also this behavior, this social behavior. And I would like also to prove 10 different sizes and 10 different density of these obstacles. So there are going to be 100 different conditions. And to compare this, I would like to have some variables to count. These variables are the number of cells at the beginning of the simulation, because a cell can be in the place of obstacles. So the initial numbers of cells obviously will going to change. Also, I want to obtain the proportion of aggregate cells, the size of the aggregates and the number of these aggregates, and the time of aggregation of NL cells, to compare if there are some changes in the initial conditions. So I think that's all of a general idea of I would like to do. I would like to listen some ideas, or if you can tell me something.
I think that that's a great project. Of course, there's some nice published models of Myxococcus xanthus aggregation. And so we definitely can start with those. One possibility, depending on what we hear, one of the reasons we wanted to hear from everybody now was that we thought that there might be people who have shared interests who might want to work together on projects. And so there may well be other people who are interested in collective migration, maybe not specifically collective migration in M. xanthus, where people could put their heads together and combine some of the ideas that you're putting up. I think everything that you're saying makes a lot of sense. Giulio may have some ideas. Giuliano, not here at the moment. So Giuliano has been doing a fair number of Boyd's type models with CompuCell. So those are, of course, flocking models where you have drive and interactions. And so in a sense, those might not be a bad framework to use for this. The one thing that you're looking for there is the extended cells with bending. And in CompuCell, you probably do those with links. You could hook your cells up with links and then apply and then define bending energies to try to do the kinds of things that the Dresden people do. So we could definitely talk about that. Okay. Maciek may have his own ideas about the best way to do that as well. But definitely that seems like a very practical, to me at least, a practical project to do. Julia.
Hi, Edna. Hi. If you could go back to slide number 5, please. Okay. There's a. So the slime parameter or function there, that is supposed to describe the movement of the cells. What does that mean?
Excuse me, can you repeat me the question, please?
The slime, E-slime. the fourth energy term in your table?
I was thinking that this parameter, well, this characteristic can be inserted with a chemiotaxis way.
Okay.
With a diffusion of 0, just to secrete that the cells can secrete these slimes, and then if a cells can find this polysaccharide that we are simulate, they then can follow the other cell. No?
Okay, because for certainly your model requires that the cells move in a certain way. So I was wondering where the movement of the cells would come from. And if I remember from Starus model from 2007, the bacteria, they moved, I think unidirectionally along one direction or the other. And I don't think if you want to implement the same kind of model where the bacteria can move back and forth along the axis, or it can also rotate, or I don't know exactly what the cells do. Or if you require some kind of track where the cells are more likely to move, where they have already passed. Yeah, so I think the slime will be that. So I think that would be a very important component of your model.
Yeah, definitely.
About that is the slime a scalar field or a vector field? Because if you want the cells to actually move along the slime, then you may have to have an oriented slime field. But those are things we should talk about. I think we could talk about more in the next couple of days, I hope. But I think yeah, there'd be really interesting questions about how you represent these interactions and the slime in particular, because the movement of M. xanthus is really complicated, right? The mechanisms of motility of M. xanthus are pretty complicated.
Yes, definitely.
But this idea that the cells move in a directed way, where there's a vector, which is essentially a force vector produced by the cell, is something, again, that Giuliano has been working on a lot. And so I think he could help with building models based on that.
Okay, thank you.
Yeah, but the good thing about having a very complicated component that you have to model is that you can test very different scenarios and then make prediction, okay, if the bacteria move this way, this is what you get. If you move that way, you get a better result. So having something that's unknown from the biology is actually good because it can make your model more rich and actually give more insights to the community.
Yeah.
We're gonna have Obata go now.
Thank you.
So I hope you guys are doing well. My name is Obata. I'm working on lung branching and morphogenesis, and I'm being supervised by Dr. Udarak George, who's an assistant professor at SDSU. We actually haven't started the research yet. I begin in this upcoming semester, but the professor has been researching for a while. So I'm pretty new to this, and I actually haven't done any prior modeling, especially in biology. So this very much is a crash course for me. So I'm also an undergrad, which you can probably tell. As for my supervisor, she is very multidisciplinary. She has a bachelor's in engineering, a master's in math, a doctorate in biology. And as I said before, her current research is in lung morphogenesis. So some quick goals for this. We want to model this process to understand maybe why a lung would branch rather than just how, because we have been able to figure out how they branch pretty well, but we don't really understand what exactly triggers a branch. And just some things we want to take into account is stuff like FGF10 and other mechanical forces, and see how those hopefully affect the process. And our output should ideally be, a branch forming, and seeing how different amounts of whatever variable affects that. So really, why this topic? In the embryo, if we find that lung development is stunted, there's a current procedure in which you can actually block the trachea of the embryo, and that would really encourage growth of the lungs, proper growth of the lungs. And we found that it can actually increase that growth almost up to 3 times. The issue is with this procedure is it's very invasive. So for example, you'd have to go into the mother's womb and then into the embryo and then into the lung and include that trachea. And because of this, the success rate is really only around 50%. Also to what I talked about earlier, because of like the discrepancy between lung growth, where the occluded lungs grow 3 times as quickly, or up to 3 times as quickly. If we could maybe understand why there's that difference, it could help us understand why something branches in the first place. And a quick visual of this. So on the left, you have the control at embryonic day 12, and we have the 2 days after that. So you can see that in the cauterized trachea, which is the one that is blocked, the lung growth is the development of the branches is very, very quick in comparison to the control lungs. So a control lung after 1 day of development would have around 6 to 7 branches per day, while a cauterized lung is around 20. And then on the second day, you have around 15 for the control and almost double that with the cauterized. So the difference here is pretty big, and hopefully, maybe this process can help us understand what's going on. And as for the variables we chose, I mentioned FGF10 specifically because we found that it can basically turn off the process of branching completely if we remove it from the process. They've done this, I believe, in vitro tests with mice. And they just found that the lungs completely didn't grow. So we know that it's essential to growth. Other factors such as BMP, SHH, they didn't really affect it. They affected the growth, but they didn't stop it completely. So this is why I want to focus on the FGF. And also we found that if we decrease the FGF by a certain amount, we also get a relatively similar decrease in branching. And in terms of what we're looking for in branching, we're not going to focus so much on time, but rather the stopping distance between the pleural surface and the epithelium. And I'll show a visual next slide on what's exactly going on there. But the goal here is because we don't want to take time as a specific factor because it's not exactly objective in this case. So on the first row, we have the 4 pictures for elongation. So there, in branching, we found that there are around 3 processes. We have elongation, the stop, and the branching. So the first 4 pictures are the elongation phase. The next 4 are stop, and the final 4 are the branching. So we can see here L is that stopping distance I mentioned earlier. Or in this case, actually, it's just the distance between the epithelium and the pleural surface and the epithelium. Once it is here, we'll call it L naught, and that is what will be the stopping distance in that case. And we can see that in the difference between control lungs and cauterized lungs, we have a huge difference in the stopping distance, 43 microns between the two. And when we take a look at what's actually happening between the different stages, we find that during the stop and branching stages, we don't really have that much of a significant difference in terms of, you know, how much distance there is. But when we look at the elongation phase, there's a much bigger difference, and we think that's significant enough to take a look into. And maybe if we can find out why there's a difference in that elongation phase, we can understand what's going on. So what we're doing with FGF specifically is we're going to look at the flux from the accumulation of it at the pleura. So FGF10 really accumulates right here. This would be the pleura right here, and it goes to the epithelium. So we're going to look at the difference in flux between the FGF10 at the pleura and the epithelium. And just a more specific visual there. This is what's really happening. There are other factors that the professor, for now, would like me to not take into account because I am very new to this. She wants me to start with a basic model and hopefully work up from there. I'm pretty sure work has already been done at this, especially by herself and probably by other researchers. So my work is really going to be a little bit insignificant compared to everyone else in terms of complexity, but hopefully, you know, I'll learn something, and yeah, and hopefully I can learn something from you guys as well. All right, thank you.
So I just, maybe I missed it, but could you clarify what animals these experiments were done? And when you were doing this cauterizing, what is the effect of that? I understand that embryos actually will breathe or practice breathing the amniotic fluid. And does the cauterization prevent that? Or just give us a little bit of background on your experiments or the experiments that you're trying to understand better.
I believe this was done on mice. I think, according to what the professor has told me, they wouldn't actually breathe the amniotic fluid, but because this would happen before that. I'm not exactly sure. Like I said, I'm pretty new to the research. This is kind of like a crash course for me. But I can look that up and clarify the next time we meet up.
So, it looked to me like those were explant experiments rather than in vivo. But maybe I'm wrong. Were those explant experiments? Was the lung tissue cut out and put in a dish to grow, or was it growing in the mouse?
I think it was in vitro.
So it was an explant. Okay.
Yeah.
So I've seen some talks. I think I actually saw a talk. So Dagmar Eber at Zurich has done some nice modeling of this process. And I think Sharon Lumpkin has worked on this as well. And so they both have models. Those are continuum models, continuum mechanical models. But if we could understand how those worked, one could definitely try to take those base models and implement them in CompuCell. So it might be worth doing a little bit of digging overnight or the next day or two to try to come up with very simple models, essentially this picture that you have here, and of the forces and branching mechanisms that are involved. Because I know there's been quite a bit of mathematical biology trying to understand the mechanisms of branching and also limitation of growth here. Because I think, if I remember right, the hypothesis here is that if you block the if you cauterize, essentially you close that vessel there, which means that the pressure inside that lumen is much higher. And so the hypothesis is the pressure, and also perhaps that you don't dilute the FGF10 that's involved with determining the growth. So I think there's been some modeling of that. And just even if there's a perfect model of it in another system, re-implementing it here will give you the ability to manipulate it in new ways. So I wouldn't be afraid if you find somebody who's done something you like as a model, bring that forward, and then we can see what we can do in terms of trying to replicate it and extend it. Okay.
All right, thank you.
So thanks for having me. And I'd like to tell you a little bit about my project. And this is based upon a recent paper that we published. And I'd like to understand a little bit better the paper in the context of doing dynamic simulations. And the particular difficulty is dealing with proliferation and contact inhibition. So let me tell you a little bit about the paper. It's about epithelial monolayer growth. And it just appeared last year. This came out of the Jeff Fredberg's group. And the idea was quite a surprising observation, actually. When you look at the aspect ratios of epithelial cells, there is an amazing quasi-universal behavior for the geometric quantity that we call the aspect ratio. I imagine that all of you, since you've been looking at cells for a while, you know what the aspect ratio is. What you have is you have the long axis and the short axis of a cell, right? Which you can abstract as an ellipse. And the ratio of the longer axis to the shorter axis, which is a number greater than 1, is what we call the aspect ratio. Okay? And so if you look at the aspect ratio of all kinds of things, you can look at the aspect ratio of cells, you can look at the aspect ratios of packings, any kind of packings, from ice flows, the way ice flows pack, to the way Voronoi tessellations pack. There's a good chance, not a good chance, what we've observed is that there's actually a universal behavior between the standard deviation of the aspect ratio and the actual aspect ratio of a packing or of a tiling. And in the case of human bronchial epithelial cells, what we see is we see a very interesting progression. So as time progresses, initially for a very, here at day 6, this is initial seeding at an air-liquid interface of these cells. You see that the cells are fairly large, and as time goes on, not only do the cells get smaller, but their aspect ratios also decreases. So initially we start here, and as time progresses, we move down this line to relatively small aspect ratios of 1.4. So we've gone from over 2 or so to 1.4. And all of these data points seem to fall on a similar universal curve, whether you are dealing with asthmatic cells or non-asthmatic cells. There are some differences between these two classes of cells, but I don't really want to go into the details. The interesting thing is that there's this universal behavior. And we attribute this to jamming. So the idea is that as the monolayer gets more dense, the cells pack more tightly. And as a consequence of the cells packing more tightly, they have less room to maneuver around, their mobility goes down, and their packing also becomes more perfect, more symmetric. So a high aspect ratio is a more random packing, more disordered packing, and then the packing gets more ordered as time goes down. So we've seen this, like I said, in many other types of situations. You see this in granular situations. We see this in epithelial cells. We actually see something like this also in fruit fly development, the germ band extension. So we see this in many, many situations, this universal behavior. which is very interesting. So some examples of this universality in packing is shown here. On the left-hand side, what we have is we have pennies randomly thrown on a table, and we've then done Voronoi tiling, tiled this according to Voronoi tessellations, and this produces a data point, I think right here. No, where's that data point? Pennies. No, yeah, right here. The pennies are right here. So they fall on this universal curve. You can also do other, this is a real experiment. We can also do very simple simulations for packing disks in the plane. And depending on the packing density, you will move from, this is low density, so this is high variability, to very low variability, to nearly perfect packing. So this also follows the line. Other things that follow the line are simulations that people have done with packing ellipses on the plane, and also ice flows like I've mentioned before. On top of that, there's been a very beautiful model that's been developed, and this is the Vertex model by Lisa Manning and Max B. And this model seems to account fairly well for what we see in the experiments. And let me tell you a bit more about the model. Okay, let's skip this slide for the moment, but this is the Vertex model. And this model is based upon an energy balance where we have an area term and P is a perimeter term, and that perimeter term appears quadratically and linearly, quadratic for tension. I was asking you about this a little bit, James. And then the linear term represents the adhesion. So what the idea is the following, that you have a bunch of vertices. Every polygon is represented by a collection of vertices, and these polygons then produce areas and they produce perimeters. Calculate the energy of that, and then you can minimize the energy by moving the vertices around and relaxing the model. It's like a molecular dynamics type simulation. Okay, and so what we can do is we can vary the various terms, these various cost terms right here for the areas and the perimeters. Simulations. So I'm showing you two simulations. One simulation is where you see that the cells are hexagonal. So this would correspond to the situation of a more ordered system, or a situation where the aspect ratio is closer towards 1. And then we have the fluid-like system right over here, where you can see that that many of the cells are far from hexagonal, and you see that there's a lot more motion. Maybe I'll show you the simulation again. So what I showed you was an initial point where I identified a particular cell of interest, and I showed how it's moving relative to its neighbors. Okay, so this is essentially what we think is going on in the epithelial cells, but well, there are difficulties, there are problems. So these are the experiments. And I can't see my mouse now. My mouse has disappeared. Okay, well, if my mouse was to be here present at the screen, I would click on this and you would see a movie, and then you would see that the number of cells is dramatically increasing because of proliferation, and you would also see those trajectories. I'm going to try one more time. Just trust me that over time, what I have here is I've got a movie that extends over 2.5 days. So initially, this is very low seating, and at the end of the 2.5 days, these cells will be packed in a very tight configuration, okay? And what we can look at is we can look at the dynamics of this process. In particular, we can look at the mean square displacement, which is this red curve, and you see that the mean square displacement increases, as you would expect, because these cells are moving around, their mean square displacement from their original point of reference. And the question is, well, are we in a jammed situation? Are we not in a jammed situation? How well does the Vertex model actually simulate what's going on? And I believe that it doesn't do a very good job, primarily because proliferation is such an important issue, such an important driver for the system. So the reason I'm here is to see if the CompuCell simulations can actually produce a more realistic simulation rather than these steady state simulations that the Vertex model produces. So the goals are for me to learn more about CompuCell and do simulations which include proliferation, and then which can also account for contact inhibition. And contact inhibition is the phenomenon or the observation that as the cells get more and more dense, more and more tightly packed, that their proliferation rates goes down. So it seems to me like this is actually a no-brainer for CompuCell. I mean, this is probably as close as anything that this could have been designed for.
The one thing that can be an issue when you translate vertex models into CompuCell type models is that in a vertex model, each edge is independently identified. And so if you have specific energies associated with individual edges, those tend to be a little bit complicated. You can do it, but they're a little bit inconvenient to translate to CompuCell. If I look at the energy functional we write down, you had a volume term, you had a term that was proportional to the total perimeter squared, and a term that's proportional to the total perimeter. So all of those terms exist in CompuCell already. If you had a term that was proportional to the length of each individual edge squared, that would be a little more work to do. So in other words, if the energy really is pi for the whole thing, as opposed to each edge length separately squared, then that winds up, that's easy to translate. If it's the length L, if it's Li squared, then it's a little more difficult because CompuCell doesn't have a concept of the individual edge being an object. You can get it, but you have to do things to it. And so if it really is the way you wrote it, that energy functional translates into CompuCell immediately. Giuliano can show you how to apply forces to the cells to make them move around with the proper statistics that you want. And Gilberto has nice statistical analyses for how to do the cell tracking for the mean squared displacement analysis. So we have all the pieces for that. I guess, well, proliferation is trivial once you decide what rule you want. So a classic, I mean, if you're really doing it just in 2D as opposed to 3D, then doing contact doesn't work because everything is in contact with everything else. But what you could do is you could do a pressure inhibition where you say that the pressure of the cell, the growth rate of the cell depends on the pressure. And if the pressure is high, the growth rate's low. So you write a Hill function of the pressure where there's a contact inhibition, whereas as the pressure in the tissue goes up, the growth rate goes down. A classic example of that would be the stuff we did with Heiko Enderling a long time ago, where he was modeling pressure inhibited growth in epithelia. So definitely these are things. Figuring out what parameters you want and exactly how to do it is another question, but at least in principle, all the mechanisms you want exist. The one thing you probably would want to do differently is you probably don't want to use the surface fluctuations to drive your cells because the amplitude of movement will be too small. And so your simulations wind up being very slow. And so you probably want to apply an explicit force with particular statistical properties to your cells, which is more how the vertex models do it. But yeah, that seems achievable.
How about the edges themselves? Would they, the vertex model is built into its straight edges, right?
Mm-hmm.
CompuCell does have curvy edges, is that right?
Yeah. Again, depending on the level of granularity of your simulation, the edges could be sort of jaggedy, or if you have very fine discretization, they get more curved. And it's like anything else. I mean, if it follows young Laplace, and so if there's a pressure difference between the cells, then the edge between the cells is curved. And if the pressure difference between the cells is zero, then it's flat. But if you want to see that, then you have to build bigger simulations with more voxels. Of course, if you're in 2D, then having a couple 4,000 by 4,000 lattice isn't a big deal. So you can have pretty fine pixel granularity.
Yeah, I think we can do roughly hundreds of cells.
Yeah. So yeah. So one of the things that I think we were going to talk, that Giuliano is going to talk about tomorrow, is how do you decide how to map CompuCell parameters to real world parameters. And so the level of detail is one of the things that you have to pick. CompuCell cells live on a fixed lattice. And so if you say one lattice site is two microns, then that says your cell, that gives you how detailed your cells are. If you say one lattice site's a 1/10 of a micron, you could represent your individual cell in a lot of detail, but of course you can't represent a huge number of cells. But of course you could play with that. You could change that. The model structure doesn't change, and you could change those things as you work. But that does seem like a very reasonable project to do.
I was just going to ask you, when you mention pressure inhibition, do you mean like the area or the volume? Like, are you going to compare that to like a static volume and then do the inhibition?
I have a question about the experiments. The very first paper that you show, how big are those cells in the Z direction? Are they getting squished and taller?
Yeah, they are actually getting squeezed.
Okay.
So how tall are they? I would say that they're roughly 20 microns.
Okay. 20 microns. Okay.
Maybe not the smallest five.
I think the one thing that confused me a little bit is I think your aspect ratio is the inverse of what I would expect the aspect ratio to be. A taller cell has a smaller aspect
Okay.
ratio.
Well, we're talking about the movement aspect ratio.
Right. So you've got yours is
We're
reciprocal.
not worrying about the Z direction.
Okay.
Or the X Y.
Oh, you mean actually elongation in plane?
Yes, yes, yes.
Okay. No, but the reason I ask about the,
I didn't catch that. Thank you.
Okay.
Because for me, when you talked about epithelium, the aspect ratio is how tall is the cell compared to its area on the bottom.
Oh, really? Yeah.
So that's just sort of in the literature, that would be the standard usage. So I didn't catch that we were talking about the basically the anisotropy is what I would.
do you think that the cells stop moving really because, do you think that the size of the nucleus is an important factor for this jamming?
Well, I think it could be actually very important because if the moving is at that place at the end, you would see that the nuclei are about the size of the cells.
Okay.
The nuclei are almost touching.
That's something that you can easily simulate in CompuCell. Add the nucleus inside each one of those cells as a compartment that's hard to, that wants to stay round, but cannot be squished, while the rest of the cell can be squished. And maybe that's the important factor for the jamming transition, or something that contributes to it.
That's really appealing. We've always thought about the nucleus
Yeah.
as a hard, more of a hard core, whereas the
Yeah.
cytoplasm.
Yeah, so you can play with those two things and see what the effect of having a hard nucleus, but that yet can be moved around, influences.
Gilberto's simulation have a stiff nuclear compartment. For his cell motility simulation. So that's, I think this one we.
And that's something that's easy to put in CompuCell and not that easy to put in. Yeah, it should be a factor. Because you have the nucleus, you have all the microtubules around the nucleus. It should be, and then it's easy to put in CompuCell, not that easy to put in Vertex. So that's very worth pursuing. That's my suggestion.
Maybe this will just go smoothly. Yeah.
I was wondering if you'd actually done any like anything experimental for like the proliferation of the cells in terms of like pH3 staining or like even apoptosis like tunnel staining, and then looked at that in correlation to the number of cells, the density of cells.
Okay, so trying to get a handle on cell death.
Essentially, yeah.
Yes. So actually, these experiments cell death is negligible.
Okay.
But there's some other things, which some other unhappy artifacts, one of which is delamination at the higher density cells pop off.
Okay. Okay, and then have you done any pH3 staining to see if like it correlates with lower or reduced proliferation as density increases?
No, we haven't done that. But we actually have done other experiments where we treated the cells with a cancer drug, mitomycin.
Cool.
Or something like that, to slow down the proliferation. So we have movies for that as well. So we can kind of turn off the proliferation. But
Very cool.
it's a tricky game, as you know, whenever you do experiments, there's these side effects.
Yeah.
If we turn off the proliferation, we can't go to high density. Right, we stable density. That's where we think the phase transition is. We're all interested about this at high density.
Cool.
So my purpose here is want to simulate the epidermal Wood-Haney dynamics. And I'm from the south, from the Texas. So it's hot there, but now it's cool here. Okay. That didn't work. And actually, my past or ongoing research area is on the just the mechanics, where mainly use the continuum mechanics or hyperelasticity to model the tissue, the organs. And my first the project is about the trachea angioedema. So this is the airway, and I model the airway swells. And this way we are just make the Newman lateral. So we are just constrict the breathing, and I model how the airway swells. Another project I'm working on is about the pregnant cervix remodeling, because the cervix experience a great remodeling in pregnancy. So I model how the cervix become large and thick, and also very short. So it's a remodeling process. And the tool I use is the hyperelasticity. And so it's a continuum. I don't care about the cellular level. But I want to go into the more just the multi-scale level and go to the cellular level for the modeling. And I found one interesting area. It's about the Wood-Haney. And so first one, the Wood-Haney is a complex process in which the skin and the tissue under it repair themselves after injury. So there is one example for the wood. So first there is the blood is very pain. And then, okay, we have the inflammation, and then we have just the proliferation. So the wood starts to heal, and then there's a scar there, so the wood is finished. So it's repaired. This is just an accident. We don't use our hand for experiments. That's painful. And so there are some stages in this one. Anyway, so the stages are not so clear. And so roughly we have 4 stages. The first one is the bleeding. So we have a lot of blood. So here. And after a while, some days, there is inflammatory process. So you can see the wood area swells and become wet and also red. Then after some time, there is proliferation. And then this area generates many fibroblasts and also some fat in this area. Okay, and it's very, very complicated, and many chemicals there and also other substances in this area. And lastly, we have the final remodeling period. Okay, so there's a scar there, and also the shape changes, but it's repaired. So in the first stage, so the hemostasis, and so mainly the blood vessels in this trauma area constrict to slow blood loss in a process known as the vasoconstriction. So just the blood vessel close. to prevent the blood loss. Then the platelets are then released on the wood side to coagulate with fibrin. So the second part. Then the aggregation of platelets and fibrin forms a thrombus, where blood clot that seals broken blood vessels and stymies blood loss, say thrombus. And for this, just the process maybe last for 2 or more days. It depends on your the damage area, how serious it is. And so we just, if we want to treat the wounded area, we cover with some bandage or other medical treatment. And the second stage, the inflammation. And this stage, the blood vessel will have dilates. Yeah, there is dilation in this area. And also a number of beneficial enzymes and nucleosides, were called the white blood cells, enter the wound area to facilitate inflammation. And so there, we can watch here in this area, they're marked by redness at the wound side, and also there is pain, swelling, and heat. And this stage can last a longer time, 6 days or more sometimes. Also, anyway, so the second stage and the first stage may be just overlapped sometimes. The second stage is proliferation. In this stage, it forms many other substances or chemicals. The formation of the granulation tissue or angiogenesis. And anyway, I just skip the details here. Also, there are fibroblast activity and collagen production in this stage. And then finally, the remodeling process for the wound healing. Okay, there's collagen production, and so we can regain the tensile strength and skin elasticity for the just the skin. Okay, and also there is a stabilization of the vascularity from the inflammation and the proliferation stages. And also there is atapsis and or cell annihilation in the wound area. Okay. Anyway, so after the remodeling, the skin repaired, but it's different from the original skin. There is maybe a scar or lose the elasticity in this area. And so there are many challenges for biology also here for the wound healing. And the mechanism for the epidermal migration is still only partially understood. Okay, it's very complicated. And the normal epidermal cells are non-motile, so not moving. However, in the neighborhood of the wound, they undergo marked phenotype alteration that gives the cell the ability to move via finger-like lamellipodia. Okay, so in the wound edge, so the cells are changing very fast and move very, very fast. And so there are many other factors influencing the wound healing, like the contact inhibition and by the growth factor, and or like the contact guidance, and also mitogenetic effects or cell division. So anyway, so many important activities occurring in this area. Also for the spreading of epithelial sheet, so there are maybe many, yes, some kind of mechanisms we are not can understand about it. Yes, the first one is the rolling mechanism. Second one is the sliding mechanism. The rolling mechanism, it's like the cells are rolling to the edge to close the wound. Another one is the sliding. The cells just slides and pulling by other cells into the wound edge to close the wound. And also, so the cell mitosis is non-uniform in the wound area. Okay, after injury, so there is no immediate increase in the rate of cell generation, just as the other normal area, so not too much change. But soon after the onset of epidermal migration, mitotic activity increases. So the cell division occurs very fast. And also there is some data here. The greatest mitotic activity is actually at the wood edge, where it can be as much as 15 times the rate in normal epidermis. Okay, so very, very large amount there. Also moving outwards, activity decreases rapidly across the band. Okay, so anyway, so in the wood edge, very fast. Beyond that area, it's very slow. Also, there are two factors involved. The first one is absence of contact inhibition, and also the change in cell shape that both happened. And like other talks here, also the cells will change shape from very symmetrical to very flat. Also, there are growth activators and inhibitors. Yeah, epidermal growth activators and also inhibitors both occur for the wood healing. So they are just counteract with each other. So for a simple model, this one, okay, it's like a field model. We don't care about the details of the cells. We only care about the cell density and also the chemical concentration. So the field variables. We use N for the epithelial cell density and also C for the concentration of the chemical. And so the model is based on this one, the relationship. The rate of change for cell density N based on three components. The first one is cell migration. So cell will just move. Second one, the mitotic generation. So cell will just has the division to have more new cells. Also, we have the natural loss for the cell death. And for the rate of increase of chemical concentration, C, also three components. The first one, so diffusion for the chemicals. Second one, yeah, the chemicals can be produced by the cell. Last one, the decay of active chemicals. So that A and C have similar mechanisms. For this, the cell, the first one, the cell, the rate of change to time. And also we use the Laplace operator, so the delta squared N. And also the cell migration and also cell division mitosis and also cell loss. The same for the chemicals. Just also we use the diffusion here, Laplace operator, and also the cell, the chemical production, and also the chemical loss minus lambda. Here we have two functions, S of C and F of N. This one are from the just experiments. So we design the functions for S of C. S of C also have two parts. One is for activator, one is for the inhibitor. So they are different. And their curve is like this one. For activator, increase, but there's a limit. For the inhibitor, so it's decrease, and also there's one limit. Yeah. For the F of N, also one is for activator and one is for inhibitor. Activators increase, then decrease. There is a limit. For inhibitor, and then we have the increase, it's linear for this one. And this is a very, very simple and a basic model. And our purpose here is to make the model more complicated and more realistic. So we want to add more components into the model to make the cell density and also chemical concentration more realistic. Yeah, so that's my purpose here, to use the software for the cells to work on this model. So I'm new to this area, so I want to learn something, learn the cell functionality and also the software and for future modeling. Yeah, that's my purpose. Yeah, thank you.
Question, which is you showed a very detailed mathematical model. What are the results of that model?
Okay, so the results. So they have the results and the curves, the numerical results. So there's a traveling wave to the cell density and also the chemical concentration. And so in one book, and they performed the traveling wave analysis to the equations. Yeah.
The first thing you definitely want to do is replicate that model in CompuCell. In other words, I think everything you showed there, you could do inside of CompuCell. And so you'd want to replicate exactly that model and get the same results in CompuCell first. And then you could think about adding explicit cells and seeing how it changes.
Okay.
So this actually comes back to Stefan's question earlier, which is why do you decide to use cells versus a cell density field, for example?
Mm-hmm.
And so here you have a density field model, which is fine, and you'd want to be able to replicate that, and then you could say, now if I replace the cell density model with explicit cells, what happens? How does it change?
Mm-hmm.
But to begin with, you want to replicate what you've got, because you want to know that you've got the same thing, and then you can extend it. So we should talk offline, we'll talk about a little more in detail about what you're trying to measure and what the purpose of it is. But I think it's good that you have a detailed mathematical model. So Stefan, do you have a comment?
Well, my question is, what are the measurables? What actually do you measure? You have all these experiments. You told us sort of a general narrative of what's going on, but I haven't seen any measurements.
Measurements.
Yes.
Measurements. We can measure the parameters. The parameters, like here's the D, or
So you measure the chemical concentration,
Yeah.
you measure cell density in the womb. Is that
this one are
vitamin C? Is that
yes, these ones are from the maybe clinical observations. They can just estimate the parameter values. Yeah.
you have measurements for N and C?
Uh, yeah, kind of. Yes, estimation roughly.
Yeah, that seems like a challenge because you don't have good data, right?
No.
So following on James, the chemical concentration can be put directly in CompuCell as it is. There is a way there are diffusion solvers that can basically implement that. And I think there's also reaction kinetics solvers that can actually implement the S function or F function of the chemical concentration. Of course, the cell field concentration have to be completely redone to do for actual cells and when the cells stop growing, right? That is one of the functions that you have there, and also have a rate for cell death that you may want to be explicit or random as you wish. But what I would like to point out is that 2 years ago, there was a student here in this workshop, Angela Pisco. She works for, which lab is? A big lab in UK, doing dermal wound healing. And she made a model for wound healing for the skin, but she did the cross-section of the wound with cells with fibroblasts switching, and one of the results of her POTS model, the cellular POTS model in CompuCell, is that the fibroblasts have to actively migrate towards the wound in order for it to close. While in the dermal homeostasis, and growth, the migration of fibroblasts, the explicit migration was not necessary. So maybe you can jump directly into your model, and I think you're gonna do this in a plane, looking at the skin from up, right? But her model is already published, and maybe one of the things that you can also do in parallel is try to replicate the results of her model for the wound healing part, which is not from the top view, but actually seeing the wound from the side. so you can actually see the deep of the wound. So I just want to bring the attention that there's already a CompCell model published that also looks at the wound healing, but from a different perspective.
Mhm. Okay, there is also dermal, the deep dermal wound healing process. Yes.
Yeah.
The cross section.
Yes, across.
Axial.
You're interested in the plane, right?
Anyway, I can also do your idea. So cross section, so deep.
Okay.
Yes. So, but I will think about that.
Right.
Yeah, thank you.
Good evening, everyone. I'm Jairaj. I'm a third-year PhD student at Washington University in St. Louis at Dr. Pathak's lab. And my current project that I'm working on is modeling 2D to 3D migration of epithelial monolayers. So the idea is that epithelial monolayers that are plated on substrates then go ahead and invade into 3D collagen gels. And I'm trying to model the mechanics behind it and a couple of things that I'll talk about. So just some background about collective migration. So I'm pretty sure all of us here would know the importance in morphogenesis. There are a couple of examples. Then there is the Drosophila egg chamber. Like we all know that. I'm gonna skip it. Then of course in disease, which is basically what is more relevant to me and what I'm trying to look at more, is when epithelial monolayers undergo EMT, undergo ECM degradation, cross over into vasculature through blood vessels, and there is metastasis. So I'm mostly interested in the parts where there is EMT and degradation into the underlying ECM. And that's what I'm trying to model here. So, and in the invasion that we see clinically as well has been shown to be collective, as you can see on the image on the left, and even in vitro experiments where 3D cancer spheroids, we can see formation of these. Okay, we didn't mouse go. We can see formation of these strands, and that's how they migrate. And this kind of migration phenotype is what I'm trying to model. So some background on what has already been modeled. On the right is model show that Dr. James showed here. So this is basically tumor. This is tumor growth in vascular. This tumor growth in vasculature, and on the left there are a couple of examples of people modeling invasion using POTS models. So this one is just invasion into a collagen concentration, and we can see these nice invasion phenotypes. These are trying to simulate 3D spheroids, but using 2D simulations. And they're trying to migrate to model like a slice of the. They're trying to model a slice of the tumor and how that tumor invades. And the third one is actually shown here. Is actually shown that without any gradient in the ECM concentration, just the presence of these green fibers can also induce these migration invasive phenotypes. So my aim is to model collective invasion into a 3D collagen matrix and capture these various modes of migration and the effect of the ECM and the inherent cellular properties on this invasion. So some of the observations in this regard have been that there are basically three kinds of invasion that can happen. They can happen in like collective strands, like we saw in that image. They can be these detached clusters that detach from the main tumor and they go ahead and migrate. Or they could just invade as single cells. Regarding migration mechanisms, they could, so collagen 1 has a fibrous structure where that collagen could be either degraded or it could migrate through the pores of that collagen. So these are the two modes that I'm also trying to capture. Apart from that, it has been observed that the leader cells are more aggressive, actively degrade the matrix, and lead the collective invasion. It's also been shown in tumors embedded in collagen that DDR2 knockdown prevents which prevents the degradation of the matrix through that pathway. It also stalls like how these leader cells get polarized. And also biochemical gradients like SDF1, they polarize the leader cells and they also direct the migration. So there are biochemical gradients and biomechanical pathways that are involved in the tumor invasion. It's also known that cell-cell junctions strength and cell ECM junction strength, they guide the collective migration phenotype and the invasion. These images on the right show the computer simulations of like varying cell-cell adhesion strengths, and you can see different tumor invasion in these. So it's also known that the collagen 1 structure can be tuned with temperature and pH. So I'm also interested in knowing how do these properties like fiber length and collagen density affect how the migration turns out. Also inherent properties like cellular motility, contractility, protrusions, how do they affect the final outcome? So I have come up with like certain ideas that I could model. So the first thing is so I'm trying to use CompuCell 3D to model this, and I've achieved like some success in modeling some basics, but I'm definitely looking to expand that model. So the idea is to model the epithelial cells as discrete objects which can like deform, migrate, grow, shrink. The ECM can be modeled as a field, or as a concentration field in space, or by freezing a different cell type and calling that as collagen fibers. So how the initial setup is cells which can be either like a monolayer, which is mostly what I'm trying to do right now. They're embedded inside a collagen 1 matrix, and then after a certain time, they start migrating into the neighboring ECM after degrading it. So the driving force behind this could be haptotaxis, which is basically cells migrating from one ECM density to the other ECM density. So basically here, where the cells are present, there is no in that location there is no ECM, and there's ECM everywhere else. So that creates a natural gradient, a natural drive for cells to move out, migrate. And I would like to model like the strength of this degradation of how cells cohesivity, and how like all of these parameters, how can these be linked to like the actual degradation, and like for example, like cells which start degrading collagen have higher Viminton signatures, which are like more mesenchymal cells. So how does that feed back into the cell and cell ECM junctions, and modeling like these kinds of interactions? So what can be experimentally compared with is invasion distance. So in experiments, invasion distance is a known parameter that you can measure, so which can also be compared in the model. How they're trying to model like the remaining collagen, how much collagen has been degraded, that could also be compared. And cellular properties like actomass and contractility, protrusions, they can be modeled in a way such that like one parameter can represent them, something like mechanoactivation, and again those could be linked back to the cell and cell ECM junctions. So the idea would be like first, like the basic step that I followed to do it was like just have a simple setup of cells, set up a chemical field gradient, and like see if I can model just simple migration of cells along the chemical field by biasing the energy function with the chemotaxis term. Secondly, like the second step would be, instead of having a gradient, have like a uniform concentration of ECM, and then the cells which are in contact with the ECM, they start to degrade it around it, and continue to degrade more and migrate more, like that. So finally, what I would like to really model is like how on the right you see nice ECM fibers, like that sort of a representation in my model, so that they actually pose a physical barrier, confine the cell, and actually give a way to either degrade the matrix or squeeze through the matrix and migrate. And like finally, like if I can link CompuCell 3D with a different software like MATLAB or something, and I can explicitly model ECM there as like a finite element model or something, and then have the two talk to each other, that will really represent ECM more accurately. So yeah, I've not achieved success with these couple of steps. I've basically been able to just get till here, have a constant concentration, and have cells move. But yeah, so that's the idea. Thank you.
I was going to say, I mean, there's been quite a bit of modeling. I mean, people like Paul Kulesa have done modeling of this kind of phenomenon. Friedel has done it, of course, not necessarily with our methods, but it would be interesting to look at what people have done in terms of modeling the degradation of ECM, modeling leader-follower behavior, modeling polarization and collective movement. There's some simple things you could do with collective movement, which we could talk about. If you apply an explicit force where the force is biased by the direction you moved, you get collective movement. I think Giulio, certainly people have done modeling of tip cell, stalk cell selection using sort of delta notch type inhibition. So that could be done. I think Kulesa has pretty good models of that. Not in CompuCell, but would be usable. Yi Zhang has done models of migration in fiber architecture. Roland has done that. So we should look a little bit at what the, I mean, you may have already done this, but we should sort of review what kinds of models exist. Again, if somebody's built the model in another system, then that helps build it here, because at least you have an idea what the mathematical structure is. As Stefan pointed out earlier, if you don't know what you're trying to measure, what your target is experimentally, what the measurables are, that's tough. But if somebody's published a model, you could at least shoot at the model, and so that's also something you could do. So I think this idea of trying to do collective, I mean, there's some nice simulations of basically pathfinding, where a cell, you start out with ECM that basically is frozen and inhibits the cell movement. Cell has some local patch of matrix metalloprotease. It moves into that region, dissolves the matrix. That means that cells can move there, and therefore other cells tend to follow it. And especially if you have some mechanism where one cell starts moving in a given direction, they tend to continue to move in that direction. You then get these chains of cells moving along. And as I say, Kulesa has done that a lot in the context of neural crest cell migration. And I think other people have done it trying to understand lateral line formation as well. I'm trying to remember who did the lateral line simulations. But this is also a reasonable thing to do. How much fiber architecture you're going to get, I don't know. In a week, maybe not so much. But Giulio also does fiber modeling, so you could talk to him about that independently of the CompuCell things. And we could always call Yi up, and she didn't do the fiber modeling inside of well, she did some in CompuCell. She did some other, it was pre-CompuCell, a lot of that stuff. It depends on the level of detail you want. So if you want your fibers to really be 100 nanometers or less in diameter, and then your voxel resolution has to be very, very fine. If you're willing to have basically point particles that represent obstacles, and those point particles are destroyed by your MMPs, and so that's more like invasion percolation in a granular medium. Those kind of models are you can do easily, where you have the explicit, where the fibers are in the cell matrix itself. Yeah. So, but those are really interesting questions. It comes back to this question, which is, you have this biological reality, which you have to simplify. And then the question is, how do you simplify it? And there isn't necessarily a single best way to do it. It depends a little bit on the kind of question you're going to try to answer. And of course, the nicest thing is if you could have different representations and then compare them. Because of course, if you've got the physics and the biology right, you should get the same answer, whatever the representation. And so ideally, you'd like to be able to represent your cells or your ECM in different ways and still get the same result.